And welcome back, AP Calc students. Time for more free response questions from old AP exams. Today we are looking at the year 2016, question number 3. And this style of question is given a derivative graph, go through and apply that understanding to the questions they are asking. So let's take a look here. The question says the figure shows the graph of a piecewise linear function for -4 less than or equal to x less than or equal to 12. The function g is defined by g of x is equal to the integral from 2 to x of f of t dt. Now there's a couple things that could be potentially confusing here that don't need to be, but the first part here we can see we have several just line segments. And one of the reasons AP likes to use line segments is that they wind up being very easy to calculate the geometry because it's going to be the area of a triangle. So the first thing that's confusing, though, is that you can see this says this is the graph of f, but then they also define this equation. They say it is the function g is defined as the integral from 2 to x of f of t dt. Now, this is fairly common with the way AP will do things because they're testing you to see if you know your material. Well, something that should be understood by all calc students is that when you're integrating from a to b, we frequently will say, well, inside here would be the derivative, and when you do the fundamental theorem, you get the original function, so f prime integrated becomes just f, and we would do f of b minus f of a. Pretty straightforward there. The relationship of what you get out of an integral is always going to be we sometimes refer to as the antiderivative, but more importantly, what's inside the integral is always the derivative of the result, or the result of the formula, because if it's definite, you would just be getting a number, and the derivative of that would be 0, but we mean the derivative of the formula is always going to be what was inside the integral. So that's always a way to check your answer, even something simple like the integral of 2x dx. We integrate and we get x squared plus c. This is indefinite, but we always take the derivative to check our answer. Well, with that being true, I want to go up to this one. I'm going to put g of x over on this side of the integral. Now, when we do that, this relationship still holds. What's inside the integral is going to be the derivative of the result. Well, if that's true, what can be confusing from the get-go is, why is the function f inside the integral, and is it g after integrating? The whole reason they're doing this is to see if you know your material. So f is really the derivative of g, or we could call f g prime. So when they say up here, this is the graph of f, you immediately want to make a correction there, or this adjustment, and say, well, I know that f is equal to g prime. And then on the actual function itself, you could go in here and you could say, well, I'm not going to use f anymore, I'm going to use g prime. And when they do this kind of thing, you actually get a point for declaring that. And you could say, well, before I do anything else, I'm going to say that g is actually, or I should say f, rather, I'm going to say that f is actually equal to g prime. And you actually get a point for declaring that and realizing it. So that's the first thing that you want to address and say, okay, well, I'm not even going to refer to f anymore, it's just g prime and g, and that makes more sense. But then there's another issue. Once you reconcile that piece, I'm now going to take this and put this down here. I'm going to say, okay, well, if the integral of 2 to x of g prime of t dt is equal to g of x minus g of 2. The problem is, or this should be understandable, but the odd part is, what happened to g of 2? How come g of 2 was not in the original statement here? Why did they define g of x as only the integral here? Where's g of 2? That part of the fundamental theorem is not in the actual statement. Well, the reason it's not there could be one of two reasons. It could be this is just the way they defined it, and that's just the way it is. Or the other issue could be g of 2 happens to be 0, so they didn't put it there. But in either case, you have to respect what g was defined as. So there's two potential places to get confused. Just convert the other function to the derivative, do that, and then realize that part of your fundamental theorem may be missing. Okay? So now that we've made that adjustment, we are going to go to the question and proceed. So the question says, does G have a relative minimum, relative maximum, or neither at x is equal to 10? Okay, so this is the graph of the derivative. They're asking us what's going on in the original. Well, something you want to keep in mind, and always a good graph to have here, is let's pretend we have a function that is increasing into a flat spot or inflection point. Then the function increases, and let's say it decreases and has a minimum, something like that. Okay? And this would be our function f. Now, I'm not saying that this is that function. I'm just saying, just randomly, here's this example. I want to just quickly review graphing derivatives. And so if this is my original function, and I need to graph the derivative, I need to go to my peaks and valleys and put my handcuffs there, which handcuff it to the x-axis to tell me where the zeros of the derivative are. And I'm going to have a point here. And we go through our derivative graphing, and we say, well, the original function is increasing. If the original function is increasing, the graph of the derivative is going to be positive. The original function continues to increase, but it did hit 0 here briefly. And what happens is it bounces back up and then comes back down. So it's very important to make the connection that a flat spot on an original function creates a kiss on the derivative. Then the original function decreases, so that's going to tell me the graph of the derivative needs to be negative. The original function is now increasing. The graph of the derivative is going to be positive. And so there's f prime. Okay. Then if we move on and graph the second derivative, which we would do in blue, say, okay, well, here is the peak. And I'm going to handcuff that for that x-intercept. This one's weird. It's just right on top of itself. And then this one, this minimum, I'm going to handcuff here. And the reason I'm doing that is I'm getting the x-intercepts of my second derivative. And now I treat the first derivative like an original function. So the red function here is decreasing. Therefore, the graph of the derivative is negative. Here, the red function is increasing. So this has got to be positive, but still come back down to 0. The red function from this handcuff to this handcuff is decreasing. Therefore, the graph is negative. But I do have to get back to 0. And then from here, the red function is increasing the rest of the way. And that would be the second derivative. And if you recall, when your second derivative is equal to 0, your second derivative is going to give you the inflection points on the original function. So there would be one, and here would be another, and here would be the last one. Okay? So one thing you want to notice here is that peaks and valleys of the original correspond to x-intercepts on my first derivative. Flat spots on the original function correspond to kisses. If you continue to go through that, on the second derivative, the x-intercepts correspond to inflection points. Where the second derivative is negative, the original is concave down. Where the second derivative is positive, the original function is concave up. But you can actually answer that with just the first derivative, which is again why they like to give that to you. So let's go back to the question. We'll compare to this, and we'll be able to figure this out. So the question says, does the graph have a relative minimum, relative maximum, or neither at x equals 10? Well, if you guys look right here at x equals 10, that's a kiss. And we were discussing earlier here, kisses result in flat spots. So when you have a flat spot in your original function, that's not a relative min or max. It's just a flat spot. So so for part A, max, min, or neither, I'm going to say G has neither a relative max or relative min at x is equal to 10. And the justification of my answer is because G prime doesn't change sign. It stays negative the whole time. And so I'm just going to say because G prime does not change sign. Okay. Now one thing I want to do is going back to this derivative graph here, now that we've discussed that it's a derivative, what can be helpful sometimes is to reinforce the fact that it's a derivative, and just using the scheme of black, red, and blue, is that you can go back to this thing and you can overlap it here in red just to emphasize to yourself that it is a derivative graph. Because it's very easy to forget that, and you can start treating the derivative like an original function, and you can make careless errors, and sometimes the color coding can just be helpful there. Okay, so there it is. All right, let's continue. Part B says, does the graph of g have a point of inflection at x equals 4? Well, coming back over here, let's look what happens at the red function, the derivative, when you have an inflection point. So if we look right here, the function here is concave down and then concave up. So this point of inflection, what's going on red? Well, it's a minimum. At our next inflection point, we go from concave up to concave down. This inflection point was occurring at a maximum. The next part, it's concave down until here and then concave up, and at this inflection point, it's a minimum. So what you should be noticing is that, yes, the second derivative goes from positive to negative, but that's corresponding to maxes and minimums on your first derivative. So where your first derivative has peaks and valleys, those are corresponding to inflection points on your original function. So what this question is asking is, what's happening at x equals negative 4? Well, since we have this here, all of these points are kind of relevant here. So let's look at the original function first. Let's go back and do the x-intercepts. Let's see what's going on here. So my first derivative right here at negative 2 is going from negative to positive. Well, if you look over here on this graph, when we're going from negative to positive on red, red is going here from negative to positive. It's creating a minimum. So right here, I know that this value right here, I'm just going to put R min. Okay. Now this next spot, this would correspond to a kiss. That's just making a flat spot, so I'm just going to put the word flat, much like it did here. This kiss here corresponded to that flat spot. Then I kept going. Here was another x-intercept. Well, that's going to be important. But when I go from positive to negative, that is like the derivative. Where are we at here? On this one, we're going positive to negative. Right there, positive to negative, that was a maximum. So I know that this is going to be a maximum value. And then right here I have another kiss, which is a flat spot. So that was from maxes and mins. Now these other points here, you don't want to get confused by them. They're important, but it didn't have to do with maxes and minimums and flat spots. That is always by the x-intercepts. But now the next part of the question, which was, what about the inflection points? So if you look here again, the minimums and maximums of my first derivative correspond to inflection points. So every time I have a maximum or minimum on my first derivative, this is going to be an inflection point. So right here is an inflection point. Right here is an inflection point, 2 maxes. Right here, this flat spot was also an inflection point, just like here. When you have flat spots, you have inflection points. Right here, I have another inflection point. And right here, I have another inflection point. So this problem actually had 1, 2, 3, 4, 5 inflection points. And in fact, if you wanted, you can always just kind of sketch a potential graph here. If we graph this, this is decreasing. I'm going to do this off to the side here. The problem is decreasing to a minimum, and then it's increasing, and then there's a flat spot, and then it increases to the maximum, and then it's decreasing. There's another flat spot, and that's the graph you have right there. So this would correspond if we, like, for example, said, here we go, negative 4 all the way to this. Let's just, this is just a possibility. This value right here, we could say that was 12. Then that would mean that our minimum here, this would be occurring at negative 2. And our flat spot right there, that's occurring at positive 2. And our maximum is occurring right there at 6. And our next flat spot, let's see. Yes, our next flat spot is occurring at 10. And then our the end of it being 12. Well, if we did it that way and we looked at inflection points would be something like this. We would say, well, this is concave up, and then somewhere in here is an inflection point. and then we go concave down, there's an inflection point. We go concave up, there's an inflection point. Concave down, there'd be another inflection point. Concave up to this last one, and then concave down. So you can see I've got 1, 2, 3, 4, 5 inflection points, and I've got 1, 2, 3, 4, 5 peaks or valleys on my first derivative. So you don't have to know how to do that. I just thought I'd throw that on there just to look at it. So let's see what the question says again. Part B says, does graph of G have a point of inflection at x equals 4? Justify your answer. Well, at x equals 4, there we are, 4, 4, and that's a peak, and the answer is yes. I can say yes, that is a point of inflection. I'm going to say yes, x equals 4 is a point of inflection on G because G prime goes from increasing to decreasing. G prime here, increasing and decreasing. Okay, in other words, it's making a maximum. So it's going to have an inflection point. Okay, part C. Find the absolute minimum value and the absolute maximum value on G. Well, when you guys hear a min-max question, you guys should be thinking, well, I better get my critical numbers. And how do I get critical numbers when my derivative is 0 and undefined? Well, here's the only part you got to check. When's my derivative 0? You have several points here that we're going to have to check, but we don't have to check all of them. But critical numbers, and I'm going to put in endpoints. We're going to have to check. So my endpoints are -4 and 12, got those. And then let's investigate the critical numbers. Now the critical numbers that have potentials to be maximums and minimums are only where it's crossing, because when it's kissing, it's a flat spot, and flat spots don't make maxes or mins. They're just pauses. So I don't need to worry about 2, and I don't need to worry about 10, but I do have to worry about -2 and 6. They're relative mins and maxes, but they might be absolutes. We'll have to check. So we have 4 potential candidates we have to look at. So we are going to have to investigate when x is equal to -4, that endpoint, -2, that critical number, +6, that's a critical number, and then the endpoint 12. Okay, and now we have to go back to the original question here using the defined g function. So let's try -4 first. So what is going on at g of -4? Well, and actually I think just for space here, I'm going to get rid of this graph here. And let's move these points right here. I'm going to say x is equal to -4, -2, 6, and 12. And then we'll just give us a little bit more space here. So let's investigate g of -4. Now, according to the rule, what that is defined up there, and I'll sneak this in right here, it is defined that g of x was equal to the integral from 2 to x of f of t, but we replaced f with g prime of t. So g prime of t dt. Okay, so there's our rule that we have to use. Okay, and so I'm just trying to figure out what's going on at g of -4. So g of -4 is going to be the integral from 2 to -4 of g prime of t dt. Well, a always has to be less than b, so the fact that this is negative is messed up here. So I have to switch the order. And whenever you switch the order of a and b, you just put a negative out front. So now this is the integral from -4 to 2 of g prime of t dt, or we can switch it to x, doesn't really matter. Okay, well now it's time to use the graph, and now it's going to be time for geometry. So we're going to integrate geometrically from -4 to 2, so from -4 to 2 of g prime, and here's the graph of g prime. Well, we're going to be doing a lot of geometry here, and we have all sorts of triangles, so we might as well knock all these out. There's a lot of symmetry, so this actually goes pretty easily. So we have this right triangle right here, the very end. So we're going from -2 to -4, that's 2. This height is 4. 2 times 4 is 8. Times a half is 4, but we're below the x-axis, so I'm going to put a -4 right there and circle it. Okay. My next triangular area, I'm going from -2 to +2. This is 4. My height is also 4. 4 times 4 is 16 times a half. This is above the x-axis, and it is equal to 8. This next triangle looks symmetrical, and it is. We go from 2 to 6, which is 4, and the height is 4. So this one also is 16 times a half, which is 8. So those are the same. And then this next one looks also very similar, just below the x-axis. 6 to 10 is 4. This has 4. So it is the same, except below the x-axis, which makes the area negative. And now we have this last little chunk, which is just like the first chunk. 2 times 4 is 8, times a half is 4. Below the x-axis, we're negative 4. So we have all of the areas there, and we're going to need those as we compare integral symbols with the geometry. So let's see, what's going on from negative 4 to positive 2? Well, if we just look at the graph, from negative 4 to positive 2, we have a negative 4 area plus a positive 8 area. So I have the negative from the integral here, and I get negative 4 plus 8, which is a negative, or which is 4, with the negative is going to be negative 4. Okay. So we've got that endpoint. Okay. So now let's move to our next point you have to check is g of negative 2. So g of negative 2, that's going to equal the integral from 2 to negative 2 of g prime of t dt. Once again, a has to be less than b, so we got to throw a negative in front and swap our a and b value. Okay, and now it's back to geometry. From negative 2 to positive 2, that's just this triangle that's 8, but there's a negative in front here. So it was 8, but with that negative, we're getting negative 8. Okay. We have that one. Now we have to check positive 6. So g of 6 is equal to the integral from 2 to 6. Well, a and b line up for the first time here. Okay, so we're just going from 2 to 6. So from 2 to 6 is just 8. That was very easy compared to the others. Okay, so we had a negative 4, a negative 8, now a positive 8. And the last one we're checking is g of 12. So we're integrating from 2 to 12 of g prime of t dt here. And let's see what we get from 2 to 12. So we get this triangle, which is 8. We get this triangle, which is negative 8. So now they've canceled out, we're at 0. And we have this last little guy, which is negative 4. Okay. So the final answer that they want to know is find the absolute maximum minimum. So we're looking at negative 4, negative 8, 8, and negative 4. So pretty clear that the absolute minimum will start there. The absolute minimum is negative 8 here, but we'll say occurs. Absolute minimum occurs at g of negative 2, which is equal to negative 8. And the absolute max occurs at, looks like we have a g of 6, which is equal to a positive 8. So there are our two answers there. Now make sure you don't just make an assumption here. It turned out on this one that the relatives and the absolutes did turn out to be, the relative maxes and mins turned out to be the absolute maxes and mins, but that doesn't always happen. It's very easy. In fact, if I draw a small version here, when this question started, it was decreasing to its minimum, and then it was increasing, and we had that flat spot, it was increasing, and then decreasing again. It's very possible this last spot could have been the absolute minimum. It turned out not to be. This relative was higher, so when it ended, it must have been more like that. But it's also very possible, before it decreased into its minimum, this point could have started much higher than what turned out to be the absolute max. So that you do have to check them. It's very important that you do that. So there are those values, and the justification is all your work up here, which is fine. Okay. Now, last part, part D. It says for negative 4 less than or equal to x less than or equal to 12, find all the intervals in which g of x is negative. Well, this is this is a little bit, can be a little bit peculiar and not real intuitive. And the reason is the definition of g starts by the integral at 2. And so once you get after 2, integrating past there, it is intuitive, but prior to that, it can be a little bit confusing. So don't let this part discourage you or dissuade you, but it is a little bit confusing. So to give myself some room here, I'm going to get rid of this graph. And then we're going to, I think we can leave that there. Okay, so let's look at what they're saying here for D. So D says, find all the intervals in which g of x is negative. Well, if we look at this initially, we do have some values to start. In fact, g of -4, well, that was negative. So I guess we could start there. And at -2, we also have a -4, or we have -8. So you can clearly see that if we integrate in this interval, we're getting negative numbers. What happens if we integrate from -2 to 0? This is where your instincts can fool you. So what I recommend doing on this one is just actually, let's go ahead and calculate some of these values, and then I think you'll start to see it. So we have what's going on at g of -4, g of -2, and I'm just going to actually calculate g of 0 and g of +2. And 4, and we can do those pretty quickly here, and I think you'll see where we're going. It's easy to make a wrong guess here. So what if I wanted to figure out what's going on at g of 0? According to the rule up here, I would be going from 2 to 0 of g prime, I'll go x dx, and again we're going to have to switch that around. So we're integrating from 0 to 2 of g prime of x dx, and these go pretty quickly because we've done all the work with the areas. So let's see, the integral from 0 to 2. From 0 to 2, that's just this right half of the triangle. And the whole thing was 8, so this would be 4 with the negative out front, so I'm going to do a -4. Okay, and then I'm going to see what's going on at g of 2. Now that one, your instincts can start to kick in. Because you look at this and you go, oh, wait a second, look at my interval, I have no width. So the integral of that is going to be 0. So what I want you to see is that when we go from -4 gave us -4, -2 gave us -8, 0 gave us -4, but when we got to 2, we got to 0. So the question is, when is g of x less than or equal to 0? We are negative up until we get to 0. Until we get to 2, and then it is 0. And this is why it goes against your instincts. If you'll notice, you would think, just by looking at the picture, that if you integrated from -4 to 0, you would think, well, doesn't this negative triangle here knock out this triangle here? Well, it does if we don't take into account initial conditions, and that's why you have to respect whatever the rule is here. And that's why it goes against your instincts. So many students assume that, oh, once we got past 0, it must be positive here. But actually it's positive all the way to 2, because the way the integral is defined. So that's where it kind of goes against your logic here, and it's easy to make a mistake. So far, we are negative from, I'm going to actually draw a little number line right here, just to keep track of this. So this was -4. So all the way up until 2 was when we got to 0. Okay, so I'm going to say it was negative. All right, and then let's see what happens as we go from 2 to 4. Well, now your instincts should kick in, and they're okay. So from 2 to 4, you can see it's positive. From 6, you get 8. And if you wanted, we can just go ahead and do this since we're here. G of 4, now we can just look at the graph. You wouldn't even need to check these by doing the integral. You can just look at the graph. And you'd say, oh, well, 2 to 4. Well, the integral from 2 to 4, that's half the that triangle, so that'd be a +4. So it looks like we're positive. And then we continue to be positive. In fact, when you integrate from 2 to 6, it's just that triangle, which is 8. Well, now if you look at it, when is this +8 going to get negated? Well, when we get to 10, this -8 will knock out that 8 and we'll be back to 0. And then the last part here is going to give us a negative again. So between 2 and 6, we got positive values. Between 2 and 10, I should say. Between 2 and 10, we got positive values because we had this triangle and this negative triangle here. But when you got to 10, it got back to 0. And then this last little part here is negative again. So it says that what are the intervals that g of x is negative? It would be from -4 to 2 and from 10 to 12. And so we'll say g of x is less than or equal to 0. And I'll just do interval notation here. I'll go from -4 to +2 and from 10 to 12. Okay. And again, if that kind of confused you, most students are okay getting the second interval, but this first one kind of throws them. So a little bit unusual, not too bad. But that's AP Calc AB 2016 number 3, derivative graphs. All right. Thanks for watching. We'll see you next time.